Welcome everyone to this week's session on latest in Bitcoin tech. Recently, Bitcoin Core V31 V0.31 introduced cluster mempools, merged and introduced cluster mempools. It's a significant change in the way in which transactions in the mempool um, are reasoned about. So we'll it has been in development for I think like 3 years. The first cluster mempool theory was put forth in 2023 by SEPA, that is Peter Boole, and people have been working on this theory for 3 years. And recently it has been merged into core V0.31. We'll not go deep into the cluster mempool theory, but we'll try to get a working understanding of what cluster mempool is and what sort of problem does it solve, and why adoption of it is a good thing. So that kind of thing, it will give you a working understanding of what cluster mempool is, but the theory itself is quite involved. Uh, People who are interested in going deep into the theory, you can look at. I can give you some pointers as to um, when it will start, where you can look into. So, so this is an example of a transaction graph that you can see here. Um, so this is let's say this is transaction A, and all the way till transaction E. There is a bunch of branching out going on here. These are all in the mempool. None of this is confirmed. So transaction A's child is transaction B, and B's child is C, and C's child is D. E also branches out from B. So now um, in the mempool, you need some way to reason about this branching structure or related transactions, because you can't look at when when you are constructing a block, you need to pick transactions from your mempool, and when you are picking transactions from the mempool, you can't look at the transaction in isolation or without any relation to its siblings or ancestors, because for example, this transaction B seems to be paying a very high fee rate, 25 sat per V byte, but in a mempool, you can't just pick transaction B, because transaction B's parent is transaction A, and transaction A is also unconfirmed. So you have to look at this as a package, and if you want to pick B, you should also pick A. So how do we reason about this entire group of transaction is what is called as ancestor descendant heuristics. So this is what currently exists in Bitcoin Core. So there is a particular way in which you can calculate what is the best set of transaction that you can pick, because if you look here, A to D is one set, and similarly A, B, and E can be one set. But what do you pick is the question, and there has to be some metric that that is used in order to pick which set should go in first in the block. So we'll have a brief look at how these calculations are done currently in this heuristic, using these heuristics. By that way, we can understand what are the problems involved and how cluster mempool solves for. So let's say there are like three transactions. A is the parent, and B and C are childs of A and B. What Mempool now currently does is that it will define ancestor sets for each of the transaction. For example, the ancestor set of A itself is only A, ancestor set of B is A and B, and the ancestor set of C is A and C. So first step is that it the mempool algorithm will or the heuristic algorithm will calculate these ancestor sets. As I mentioned earlier, why do we need ancestors? Because a child cannot be mined before its parent. A cannot go into a block without B cannot go into a block without A, and also you just can't pick only this and leave away this. You have to look at it as a package. So once this set is defined, the ancestor fee rate is calculated. For example, if you want to pick transaction B, you will have to calculate the ancestor fee rate of transaction B. How is it calculated? It's simple. Because the ancestor set of B is A and B, we have to calculate what fee A provides and what fee B provides divided by the sum of their weights. So this is the ancestor fee rate for B. So once you get this number, only that number is used in ordering the transactions from highest fee paying rate to the lowest fee paying rate, and then transactions are picked in the mempool from the mempool into the block. So the question is, what is the best package that can be included that respects dependencies? So currently mempool uses this technique to calculate ancestor fee rates, list them in the order of that fee rate that each set pays, and then picks. So this is about ancestors. Similarly, there is also a calculation involved about descendants. Why ancestors are necessary when you are including a transaction in a in a block. Descendants are necessary when you are kicking out a transaction from the mempool itself. So descendants are like when you decide to like kick out a transaction from the mempool because the mempool is full, then you just can't kick out one single transaction. So if mempool is full and you want to kick out transaction A, then you just can't kick transaction A out of it. You will have to kick all its descendants. So in this case, if you kick out transaction A, then B, C, D, E, everything has to be kicked out. So this is this descendant calculation similar to ancestor fee rate calculation. We also calculate the descendant fee rate before kicking it out. So once you so what the algorithm does, the heuristic algorithm does is that similar to ancestor fee rate calculation, it also calculates the descendant fee rate calculation and keeps a list and sorts the list, and transaction descendants which are paying the lowest fee rate will be kicked out as a full package. So the question that this heuristic tries to answer is, what is the cheapest package that can be removed without leaving a broken descendant behind? So this is a very basic overview of how or what how the current existing ancestor descendant heuristics inside the mempool currently works. um, I'll pause for a moment. If there are any questions, I'll wait to answer.
Hey Bala, in this picture, set A is being replaced by set B. Is that what you are showing?
No, no, no. In this transaction graph, there is two sets that can be formed. Set A
Hmm.
is one set of transaction that can be picked in order to include in a block, or set B can be picked in order to include in a block.
It makes sense to include set A, right? So is there
Yeah.
any chance that set B will get included? There's no chance, right?
No, it depends. This is just one. What we are seeing here is one cluster of related transaction. There can
Okay.
be another cluster of related transaction in there can be many related cluster of related transaction in a mempool. What the mempool tries to do is that it doesn't view one single transaction in isolation. It doesn't look at one single transaction and sees what fee rate it is paying, and then orders it, sorts it. It doesn't do that because it can't do that, because although transaction B is paying 25 sat per V byte, it can't only include transaction B, it has to include transaction A also. So that's why mempool spots these sorts of related transaction and tries to create sets out of it, and each each set's ancestor fee rate is calculated. For example, set A's ancestor fee rate is calculated in for example, if if it wants to include transaction B's ancestor fee rate is calculated in one fashion, like it will include fees provided by A and B. Similarly, if it wants the ancestor fee rate of transaction D will be the sum of fees that A, B, C, and D provides. So this set A will be a very high fee rate transaction when compared to set B. So set A will sit on top and set B will sit on below it, and like in this fashion it will keep calculating the ancestral fee rate of whatever set that it can come up with in the mempool, and sort them and then pick from them.
Got it. Got it. Thanks, Bala.
Yeah. So this is how um, the existing heuristic works. So we'll look at what are all the issues associated with this issue. So first things first, if you can see in this example, there are two sets. Transaction A will be there in set A and set B also. And now the issue is, let's say mempool lists set A first and set B second. Um, and then like it picks set A and then set B and puts them in the block. The problem is first set A will sit, and following that set B will sit. But the problem here is that A is part of both A and B. Now it doesn't have any problem with the calculated fee rate that it will receive when it puts set A into it. But when it puts set B into it, it will lose transaction A in this, because transaction A is already on top of set B, and one transaction can go only once in a block. So it's when it does the reasoning, it looks at two sets with let's say this set gives you let's say 20 maybe not 25, I think it will give you somewhere around 20 sats per v byte, and this set B gives somewhere around 15 16 sats per v byte, 16 sats per v byte. But because transaction A is already in part of set A and it doesn't belong to set B when it actually goes into the block, this second set B calculation, like 17 sats per v byte, it might have calculated, but when the transactions are put into the block, it will receive a lesser fee rate for this set. So that is a problem with the existing method, wherein there is overlap in packages. So this is a big challenge, and it sorts of prevents you from uh, estimating your expected blocks fee rate very accurately. So so that is one problem. The second problem is uh, uh, because we are using ancestor fee rate and descendant ancestor fee rate for including transaction in a block, and descendants fee rate for kicking out transaction from the mempool. At times these two these two metrics will might clash. What does it mean is that um, let's take this example. A is the parent, B, C, D are children. So let's assume that B is a high fee paying child. C and D are like a very low fee paying child. So when you do the ancestor fee rate calculation for B, this set of A and B will be a high ancestor set fee rate thing, because B is paying a very high fee rate, and it sort of finds its way to the top of the block, and it is attractive enough to mine A and B. Um, but when you look at eviction heuristics, D's parent is A, D, D, A. When you look at eviction heuristics, uh, A's descendant is D. So if you but this whole package as such has a very low fee paying thing. So if the heuristics wants to remove this A and D, what is the problem is that removing A and D is in direct conflict with mining A and B, because if A goes, B also goes. So this is an example where like at one end, a set of transaction is qualifies to be removed, but on the other end, if you see at the relationship, this this set of transaction qualifies to be mined. So the at times this mining and eviction heuristics can clash with each other. So this is very hard in terms of computation and ability to reason. So this is the condition in which current mempools and block template constructions are operating on. That's why that's why picking a transaction is not a very or a very straightforward task. Sorting the mempool is not also a very straightforward task. It's quite involved, and on top of this, you have to keep computing or recomputing the whole whole fee rates and ancestor and descendant fee rates as and when new transactions come in and go out. So, for example, you might have recent about this particular group of transaction, and you might have some numbers with respect to this, but suddenly there is a child to D, and that child pays for its parent. So then this whole calculation, whatever you have calculated, becomes moot, and like then you have to calculate the entire calculate this entire recalculate this entire set. And also, once you recalculate this entire set, whatever sorting that you had done or kept earlier gets disturbed, and now you have to resort the entire package. Of course, these things happen at a very in milliseconds, but it is still computationally not an efficient way to go about it. So these are some of the overlapping packages, um, mining and eviction heuristics clashing with each other, and high computations required to reason about the frequent changes happening in the mempool. So these are some of the drawbacks or issues associated with ancestor descendant heuristics. Um, so I'll pause for a minute because this is little confusing stuff. If anybody has any questions.
Bhala, I hear when you are explaining the example,
Yeah.
you are telling about you're removing A and D together. Why don't you go and remove C and D? Matlab, why don't you think in that way?
No, you can do that. The thing is that when you are calculating the as I showed here, the descendant fee rate uh, only determines what to remove. So in this example, A's descendant fee rate will be calculated, which is a sum of A, B, C, and D, and divided by all its weight. So, if, for example, like if the whole thing, if the whole package turns out to be at the bottom of the list of descendants and qualifies to be evicted from the mempool, uh, however, this whole descendant package as a whole package might look bad, but if you if you remove only C and D, it might look good. But the problem is with the existing heuristics, you cannot reason it in that way. So as you asked, why can't we go ahead and remove C and D? The problem is the existing heuristics works only based upon ancestor fee rate and descendant fee rate. It cannot reason this whole cluster in a separate fashion. It cannot like reason with A and B together, B and C together, C and D together. It cannot do that.
Got it.
Yeah. So that is a serious limitation, and that's why cluster mempool has been introduced to address all these problems. So in cluster mempool, um, the key change or key idea behind it is that you don't reason um, based upon one transaction plus its ancestor or one transaction plus its descendants. Rather, you look at the whole cluster. So last time we were looking at for example, if you are interested in B, all that we were interested in its ancestor A. We didn't care about its descendants or anything else. Similarly, if you are interested in transaction D, you will be only interested in C, B, and A. Like E is also related to B, but D doesn't know about E and it doesn't care about E. But it makes economical sense to look at the whole cluster and then reason as to whether this cluster is whether the cluster's fee rate is valid enough or is it high enough to be included in a block. So reasoning about this cluster will give you much more room to optimize transaction pickings and removal parts. So that's the key idea behind clusters. uh, so the other thing is that earlier we used to calculate ancestor fee rate set and descendant fee rate set, but in when it comes to clusters, you'll be able to reason with just one single metric within the cluster. You don't have to calculate two different things and then check whether these two different things are conflicting with each other in some form or the other. So that is another idea that clusters bring in. So we'll look at how clusters are processed. So so this is the same transaction graph that we saw here. So we are going to throw away this ancestor and descendant idea altogether, and we are going to look into it as a whole cluster. So here, what the first step after you identify a cluster is that you do something called as linearization. So why do you linearize this whole cluster? Is that you have to maintain dependency. Like you can't mine up transaction without its parent. You have to reason or calculate the economics of a transaction in relation to its parents. So so if you look here, that's why you do linearization. So if you look at this look at this example, what we have done is that we have listed all the transactions in a linear fashion. Tx always comes before A comes always before B. C and D always comes, B always comes before E, C, and D, because as you can see, B is the parent for both C and E. So here, as you can see, B is always before E and C. Of course, E can come after C or before C. It doesn't matter because E and C are not related to each other. And C should always come before D. What I'm trying to say is, in this linearization process, you can flip E and C. It will not violate the linear structure. So after you linearize, what you do is that you reason about it in multiple passes. So you will containerize these linear transactions into small containers and calculate fee rates for each of these containers. These containers are called as prefix. So so if you see uh, if you see here, so prefix is prefix A is nothing but just the transaction A. It can be so because it doesn't have any parent, and prefix B is both A and B together. If you look at it, the fee that A and B together pays is 20 sats per V byte. This pays only 15 sats per V byte. If you look at this prefix, which includes A, B, and E, it pays about it pays about 15.66 sats per V byte. If you look at this prefix D, which includes A, B, C, A, B, E, and C, it pays about 12 sats. And if you look at this whole entire thing, it pays about 10 sats. 10.6 sats per V byte. So now you have a picture as to which, if you pick which prefix, you'll pay the largest, you'll get the largest fee rate. So evidently prefix B is the choice. So you pick this prefix B as like this goes like um, this gets mm, like selected. So this becomes chunk one. So prefix B becomes chunk one. Um, so now you have three transactions left with you in this cluster. Then you go into second pass. So again, you do the same thing. You calculate the fee rate for each of the prefixes. So for A, it's 7 sats. For B, it's 4, and for C, it's 4.33. So A seems to be the highest fee paying prefix. So this gets selected. So which means transaction E gets selected, and this becomes chunk 2. Remaining is these two transactions. Similarly, you calculate it, and now if you see uh, prefix B, which includes both C and D, pays 3 sats per V byte. It is greater than 1 sat per V byte. So this becomes chunk 3. So now what you have is three different chunks picked out of the cluster. So chunk one is transaction A and B together, and it is paying 20 sats per V byte. Chunk two is just transaction E. It is paying 7 sats per V byte, and chunk three is C and D, and it's paying 3 sats per V byte. So now this whole cluster has been split into different chunks, and now you can reason about these chunks. The beauty is that this chunks respects dependencies and also respects the order. Um, Chunk one always sits on top of chunk two. Chunk two always sits on top of chunk three. So the by this you can see that chunk three is not on top of chunk one because uh, C's parent is B. So by this way, you can like the entire cluster is chunked into different sets, and this similarly multiple chunks. This algorithm will go about reasoning about thousands of such chunks in the mempool, and it can insert into this list. Let's say it from some other cluster, it has a chunk that pays 19 sats per vbyte. Now what the algorithm can do is that it can insert this 19 sat per vbyte in between these two. So now it has a better control over how what to insert and where to insert. And finally, if it keeps on inserting, let's assume that this chunk 3 C and D is the one that is paying the least sats per vbyte. It keeps on inserting here and there, and then finally it arrives at a list, and the mempool is about to is full, and it wants to evict some transactions from the mempool. Then what it will do is that it will just remove C and D transaction, chuck C and D transaction away out of the mempool. So now what has happened is that we have calculated the fee rates of chunks, and we have used the same calculation for both inclusion and eviction. So this is the change that cluster mempool brings you. Earlier we had to calculate ancestor fee rate set separately, descendant fee rate set separately, and like look at these two things together and see whether there is any conflict, whether one eviction is damaging another inclusion. But in this method you can see there is no that problem doesn't exist, or it has been solved because C and D automatically, when it gets pushed out, it is not dependent upon A and B. And also they get pushed out because they are paying a very low fee rate. And also there is no overlap here because A is only in chunk 1, A is not in chunk 3, or in chunk 2. So the calculation is clean. You can very confidently estimate what will be the what will be the fee rate that the whole block is going to give you when you keep including these chunks. So this is what we saw now. Is to summarize, we saw clusters. Clusters are nothing but a group of related transactions. Then we saw about linearization. Linearization is it gives you a valid mining order. It ensures that no child is mined before a parent or put before a parent. And we saw the concept of chunks, which are used to uh, separate a good set of transactions from a weak set of transactions. So this is a summary of brief summary of what the cluster mempool process is. So I'll wait for a few minutes if you have any questions, clarifications.
So, thank you, Bala. So, in essence, this is how transactions are selected from the mempool and processed. That's essentially what is happening on the mempool.
Yeah. This is the new one introduced in uh, Bitcoin Core version 0.31 onwards.
So, before now, I guess this is like an eviction strategy based on fee rate. So, before now,
Yeah.
is it mean there were no ancestor transactions? Okay, there was no option for um, um, using maybe child transaction that has a parent transaction if each transaction was just independent, and then eviction or inclusion was selected based on those fee rate.
Yeah, currently before V31, eviction and inclusion is decided based upon uh, ancestor fee rate and descendant fee rate. So if you want to include a transaction in a block, then its whole ancestor set is calculated or looked at, and that fee rate is computed. Similarly, if you want to evict a transaction from the mempool, its whole descendants are looked at, and what fee rate that the whole descendant set is a whole descendant set is offering you. Based on that, this decision is made.
Okay, thank you. Thank you.
Yeah. So this is cluster, how the cluster mempool process works. Of course, this is a very simplified description for basic understanding sake. If you go deep into it, there are a lot more um, abstract math heavy stuffs involved. So, for example, how do you group transactions as clusters? You have to use directed acyclic graph math in it. Then how do you once you define a cluster, how do you create topologies, subsets out of it? For that, topological subset math is used. And then how do you construct chunks recursively, because transactions are keep coming in and going out constantly. The mempool, it's in a constant flux. So there are mathematical constructs used to construct these chunks. Then you draw the fee rate diagram geometry. That is also quite involved stuff. And then there are established techniques to compare the valid orderings. So what we saw is a very simple toy example, but the actual real implementation stuff is much more involved uh, than what we saw. But whatever we saw helps you understand um, understand what cluster mempool is. So as we saw, it solves some of the problems that we saw earlier. So we are not reasoning about one single transaction anymore. We are reasoning about the whole cluster, and also we are not using two fee rates to decide upon what goes in and what goes out. Now we are using only one single fee rate, which is the chunks fee rate. And now because of this construction, inclusion and eviction have become mirror images of each other. So this becomes one single list. There are no two different lists based upon ancestor fee rate and descendant fee rate, as we saw earlier. And in this list, what is in top gets included, what is in the bottom gets evicted. And this eviction doesn't disturb the what is going to be included. So that is another key improvement that this thing has brought. um, so the overall idea is to make mempools much more efficient, mm, so that there is a fair chance for people who are trying to broadcast their transaction, and also small miners who are like trying to trying to construct a block. So uh, uh, prior to cluster mempools, different big miners have their own algorithm with respect to mempools. They have their own optimization with respect to mempools and etc. Because they can afford large computes, they can afford um, engineers who can keep working on the algorithm. But if you are relying upon coarse earlier ancestor fee rate, dissonant fee rate stuff, there is a chance that you suffer from high compute requirements, and also inefficient inefficient inclusion eviction algorithms. So in order to like democratize mempool, this is a step in the right direction. Yeah, that's all I had to share about cluster mempools today. Any questions?